Morning, good afternoon, or good evening, folks, and welcome to Unit 7, entitled Momentum and Collisions. Folks, I'm going to be honest with you, this is the third time I'm trying to record this lesson. The first time I found a mistake in the PowerPoint about halfway through. The second time I recorded the entire thing and did not realize that my microphone was not turned on. So here's hoping third time's the charm. We'll start off with lesson 7.1, which is all about momentum. So first of all, what is momentum? Momentum is a quantity of motion, which is a pretty vague way of describing it, but here's a way I like to describe it. Momentum is sort of a measure of how bad it would be for you to get hit by an object. The more momentum the object has, the worse it would ruin your day if you were to get hit by that object. Now, momentum is equal to mass times velocity, so the more mass an object has, or the faster it's moving, the more momentum it has. So if you get hit by, say, a feather moving at 15 meters per second, that's probably not going to cause you too much distress. But if you get hit by an 18-wheeler moving at the same speed, that will seriously ruin your day. So again, momentum is a measure of how bad it would be if you got hit by an object moving at a certain speed and with a certain amount of mass. Now the symbol for momentum is a lowercase p, because of course it is. And the unit for momentum is a kilogram times a meter per second, which is what you get when you multiply the unit of mass times the unit of velocity. Now this is not a kilogram times a meter per second squared, which we would also know as a Newton, and it is not a kilogram times a meter squared per second squared, which we would call a joule. We don't actually have a fancy name for the unit of momentum. Sometimes people refer to it as a Newton second, but we'll stick with kilogram meters per second. Now, one other thing to say about momentum before we move along is that momentum is a vector, which means that when you're dealing with momentum, direction is very important. So let's take a look at this skill practice question. A remote control car with a mass of 4.50 kilograms is moving north at 2.00 meters per second. What is the car's momentum? Well, this is a simple plug-and-chug problem. We will start with the formula for momentum. P is equal to mass times velocity, and we will plug in the mass of the car, which is 4.50 kilograms. And then we will plug in the velocity of the car, which is 2.00 meters per second north. Remember, velocity is a vector, so we must include that direction. Now you can grab your trusty calculator, or you may find that these numbers are pretty easy to multiply together. 4.5 times 2 is 9. Three significant figures is 9.00. The unit is going to be kilogram meters per second, which is the unit for momentum, and the direction is going to be north, which is the same as the object's velocity. So an object's momentum and its velocity always have the same direction. Now it's important to remember that the momentum of any stationary object is zero. If an object is not moving, then it has no momentum. So consider an 18-wheeler that is parked versus a butterfly that is lazily flying through your garden, just minding its own business. It may seem like the 18-wheeler would have more momentum, but if the 18-wheeler is not moving, then it has zero momentum. Any object that is moving has more momentum than any object that isn't moving. Now, of course, if the 18-wheeler were to move with the same velocity as the butterfly, then the 18-wheeler would have millions of times more momentum than the butterfly, owing to its tremendous mass. But as long as it's sitting still, then its momentum is zero. Now let's talk about the law of conservation of momentum. The law of conservation of momentum basically just says that if you have several objects that are interacting in a closed system, and if you add all of their momenta together, then that total sum of the momentum will remain constant as long as there are no external forces acting on the system. And this law will be very important when we go into our next unit, which will be on collisions. When we talk about collisions, this idea that momentum remains constant will help us solve some problems. One last thing to discuss, angular momentum. Just as velocity and acceleration have angular counterparts, so does momentum. And angular momentum is basically the momentum that is inherent in a rotating or revolving object. Now mathematically, angular momentum is equal to the moment of inertia, I, multiplied by the angular velocity, omega. We're not going to do any practice problems using this formula, but I would encourage you to go back to Unit 5 if you do not remember how these quantities work. So we're going to look at a video of an ice skater skating around. She's going to go into a spin. At first she will have her arms spread out and her legs, and now she has a high moment of inertia. As she draws in her arms and legs, she speeds up. That's because her moment of inertia decreases, and consequently her angular velocity, omega, must increase, because the product of angular momentum and moment of inertia stays the same as long as there's no outside torque acting to change her rate of rotation. And that's going to be the end of lesson 7.1. I do thank you for joining me. I hope you're taking care of yourself and doing well. Please check back in tomorrow when we'll go to lesson 7.2. Also check out, we will have a Google Doc on Google Classroom with a few questions for you to answer. Until tomorrow, please take care. Continue washing your hands, and I'll talk to you tomorrow. Bye.